Hey, my name is Austin Hutchison, and this is my video report about Lab 5, magnetic braking with Faraday's Law. The purpose of this lab was to collect observational data of a bar magnet falling through a conductive tube of aluminum foil, and then model the magnet and the tube interaction computationally, and then compare the computational predictions with the observational data. A little preview of the results. The fall time in the experiment was 1.55 seconds. The fall time calculated in the model was 2.129 seconds, and obviously that is a 37.35% error. Some of the fundamental physical principles used in this lab are Faraday's law and Ohm's law. There should be a negative in front of this in Faraday's law, but they're used to calculate the current induced in the tube by the falling magnet, and then the Biot-Savart law and Newton's second law, which are both used to calculate the force on the magnet by the induced current in the tube. So how this experiment worked, essentially what happened was a magnet was dropped through a tube of aluminum foil, and the time taken for it to hit the bottom of the tube was measured. Here's the data for that experiment. For the time, you can see right here, obviously a mean of 1.55 seconds. The magnetic moment of the magnet and the mass are both given here. They were found in lab, or they were given at lab 3. The measured foil tube length was 0.29 meters. The foil width was 0.004 meters, and then the tube, or the inner radius of the tube, was 0.015 meters. Now for some details about the model. Up here, you can see that the measured quantity, or the measurements of the tube put in right here. Obviously, that defines the geometry of the tube, and then down here, this loop basically creates the tube in the model using those measurements. And then down here, you define the properties of the magnet, obviously using the given quantities also. And then down here, it creates a visualization of the magnet in the model. And then this first function right here takes in obviously a mu vector and a magnetic dipole vector, and an r vector, and then returns the magnetic field. Obviously, you can use that at different positions. And then the next function down here calculates the change in flux over change in time, obviously, which is equal, or the negative of that is equal to EMF, which is obviously going to be used to calculate the induced current in each ring in the tube. And then over here, this whole section, essentially for each ring in the tube, it calculates the magnetic force, and then it adds up the magnetic force on the magnet into a single vector. And then down here, it finds the F net, or the net force, by adding the magnetic force and the gravitational force on the magnet. And then, And now, for these questions about interpreting the simulation, which color in the model 2 corresponds to clockwise current as viewed from above? The red corresponds to clockwise, and blue corresponds to counterclockwise. And you find this by using the right-hand rule with the direction of the magnetic dipole from the bar magnet. And then what happens to the dynamics of the system when you flip the magnet around? The direction of the current will be reversed. And then how does the time in the tube in the computational model compare to that of the real-world system? How could the model be made more accurate? The time calculated by the model was significantly longer than that measured in the real world. The experiment, the model could be made more accurate by accounting for forces other than gravity and the magnetic force, and by making more precise measurements of the tube geometry. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? It tells you when the velocity is constant for most of the magnet's time through the tube, as you can see, like right here, which is pretty much most of the graph. The net force on it is 0. Now for the discussion questions, what if the resistivity of the conductor was reduced to as close to as possible to zero, or the closest possible to zero? How the dynamics of the following magnet change? The induced current in the tube would be higher, causing the magnetic force pushing upward on the magnet to be higher, causing the magnitude of the velocity of the magnet's fall to be lower. What if the holes are slots, or what if holes or slots were cut into the tube? How would this affect the ring currents in the model? The resistivity of the tube would be higher, lowering the induced current and causing the magnetic force on the magnet to be smaller, so it would fall through the tube faster. That's pretty much it. Thank you for watching.